Now, the title of this lecture is Weighing the Universe, but as a title, it doesn't really make sense, does it? Because weight is not the proper physical thing that we can actually measure independently of where we are. It is a physical quantity, but it's not perhaps exactly the quantity that we're looking for today. So let's start by making sense of what we mean by this concept, weighing the universe. We know that weight is different from mass. Mass is a property of a body, but weight is, well, is many things. It can be defined in at least 7 different ways in physics. But the one that interests us today is in terms of the force that you need to exert on a body in order to keep it still in the presence of a gravitational field. So, in other words, my weight here on Earth is different than it would be on a different planet. So if my weight is 100 pounds or 100 kilograms here on Earth, the same mass, the same physical body, when transported, say, to Mercury, would weigh only 38% of that, because the gravitational field exerted by Mercury is smaller than that of the Earth. But if you go to Jupiter, 100 kilograms or 100 pounds on the Earth would weigh 253 pounds there. So really, weight is something that changes depending on where we are in the universe. So what we're really talking about here today is mass, a property of a body which doesn't change with location in the gravitational field. In order to understand mass, we need to understand gravity. We need to go back all the way to Newton, who over 400 years ago now started thinking very, very carefully about gravity and mass and how gravity affects mass. For example, in the famous event of the apple falling on his head, and thereby giving him the idea that gravity is what pulls the apple down from the tree, but at the same time is the same force that keeps, say, the moon in orbit around the Earth. And that story might not have been true. Newton himself recounted it many, many times, and the story got better with the telling, so clearly Newton understood it was a great foundational myth of this great idea. Whether or not he ever sat under that tree and ever had that apple fall on his head is neither here nor there. The idea is that he realized, actually, that the gravity that was attracting the apple is the same gravity that would attract a cannonball shot from a cannon at a certain speed, and the cannonball would fall off after a little flight. But if we shoot the cannonball with a higher speed, then it goes a little bit further. And if we shoot it with a high enough speed, it will go all the way around, keep falling, and always missing the Earth, so never quite falling to the ground. We would shoot it in orbit. This is what happens to the moon. The moon is in orbit around the Earth. It's going fast enough around the Earth that it keeps falling and it keeps missing. So it's a misnomer to say that, say, on the International Space Station, there is no gravity. There is gravity there. Only people appear to be floating. They are floating, not because there is no gravity, but because they're in free fall. They keep falling and they keep missing the Earth as they go around. But that was Newton. In order to understand the kind of gravity that we're interested in on cosmological scales, we need more. We need Einstein. Now, Einstein came along 100 or so years ago with a revolutionary idea about the nature of gravity and the nature of reality. In order to understand Einstein, we need to do a little thought experiment. And so imagine a rocket in deep space, and that rocket is accelerating upwards with an acceleration which is the same as the acceleration due to gravity here on Earth, 9.6 meters per second square. And you've got a little ball inside the rocket. And so if you are inside the rocket and the rocket is accelerating upwards, the ball will appear to accelerate downwards to you, exactly the same way as the ball would fall downwards with the same acceleration on the surface of the Earth. So Einstein, while considering the situation, realized that actually there is no way to distinguish between you being inside the rocket and the rocket accelerating upwards, or you being inside a closed chamber on the surface of the Earth and gravity making the ball fall downwards. If you are inside the sealed container, there is no experiment, he said, you can do to tell the difference between these two situations. So that seems all right. That doesn't seem quite so profound, except now let's replace the mass, the massive particle or the ball, with something massless, without mass, such as a photon, a particle of light. If we now shoot a photon horizontally in the rocket, as the rocket goes upward, we are inside the rocket, the trajectory of the light beam will appear to curve downwards to us, just like that. But if Einstein says there's no way we can distinguish between us being in the rocket in deep space or us being on the surface of the Earth. It follows that a massless particle, like a photon, must curve downwards on the surface of the Earth as well. The situation must be exactly identical, because if it weren't so, that would be an experiment that we could use to tell the difference. And Einstein, in the form of his equivalence principle, tells us that this is impossible. So the equivalence principle then is a very profound idea. And the idea is that massless particles, such as the photon, do react to gravity, do feel gravity, despite the fact that they are massless, something that we could not understand using Newton's ideas about gravitation. And so Einstein goes further. Einstein realizes that space and time are not two separate entities, like Newton thought they were, but actually they are joint, they are malleable, they are dynamic, and they are one thing called space-time. Space-time reacts to the presence of mass by changing its shape, by changing its geometry, if you like. So the space-time continuum in the presence of a massive body such as the Earth bends and changes shape. And other bodies, including light, which is massless, traveling through space-time, try and follow the shortest possible trajectory. But in a bent space-time, say the moon, which tries to go as straight as it possibly can, follows a curved orbit, because a curved orbit is the straightest possible path in a bent space-time. So this changes completely our understanding of gravity. Gravity is no longer a force. Gravity is geometry. Gravity is the expression of the shape of space-time. And so if this is true, then light traveling through the universe, in virtue of the equivalence principle, will feel gravity, or rather the shape of space-time. And so if you have a distant star and a light beam traveling straight through the universe, as it grazes the rim of the sun and it feels the curvature of space-time due to the sun's presence, it will change trajectory. It will be deflected by an angle here that can be computed according to general relativity. That angle can also be fudged in a way by trying to compute the same value using Newton's laws of gravity, which is not quite right, because we know the photon doesn't have mass. But nevertheless, you can try and make a calculation, and the two angles are different. And so when Einstein came up with this idea, he needed a way of being able to test it. He needed a way of telling the scientific world, and therefore the world at large, whether or not his ideas about gravity were right. And an opportunity came along in 1919, a total solar eclipse. We cannot see stars and their light grazing around the edge of the sun during daytime, obviously, but during a solar eclipse, the disk of the sun is obscured. And so two teams were sent out by the Royal Astronomical Society here off the coast of Brazil and here near the African coast, in order to measure the deviation in the position of the stars in the sun around the sun during a total solar eclipse in May 1919. And when the results came back, Einstein theory was right. Einstein had correctly predicted this incredible result, which in November was on all the front pages of all the newspapers in the world. The New York Times had an article starting like this: "Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seem or were calculated to be by Newton." But nobody need worry. So that's all right. So Einstein was right. And this is extraordinary proof that his ideas about space-time geometry are correct. But if we now take these ideas and try to translate them to the universe as a whole, then we need to use some new concepts. And in particular, we need to understand what is the content of the universe, what is out there. Because if we're trying to weigh the universe, by which I mean measuring its mass, then surely we must start by looking around us and trying to count how many stars, how many galaxies, how many stuff is there out there that we can see, and try to come up with a number for how massive it is. Well, that seems easy, except when you realize there is a great deal of stuff out there. So here is an example, a patch of the sky, and here is the full moon to scale, to give you a sense of proportion. We're all familiar with how big the moon appears on the sky. And what we are interested in is this little patch of the sky, which is tiny. It's a little square which would fit inside the eye of a needle held at arm's length. So it's really, really tiny. And it doesn't look like much if you look at it like this, except if you put on some powerful pairs of glasses, say the Hubble Space Telescope, this is what it looks like. So inside of this eye of the needle, you'll find 5,500 galaxies. Each one of the dots on this picture is an entire galaxy, which contains about 300 billion stars. Incidentally, about the same number of neurons that are inside your skull, which I find a fascinating sort of numerology thing to know. And indeed, each one of those dots is a galaxy. You can see a beautiful spiral galaxy here. There are 5,500 galaxies in the eye of the needle, multiplied by the surface of the sky. That gives about 50 billion galaxies in the visible universe. So there's a lot of stuff out there. But actually, perhaps the most remarkable discovery of the last 20 or so years of cosmology is that all of that stuff is actually only a tiny fraction of everything there is. And the idea goes like this. Here is a galaxy, the nearest galaxy to us, the Andromeda galaxy. And it's about 2.5 million light years away. So it's nearby in cosmological terms, still quite far away. The light from this galaxy has left when Homo sapiens didn't walk the Earth yet, actually quite a long time before then. So the Andromeda galaxy, we can look at it, and has been looked at for many, many years. And I like to put this picture of Vera Rubin here because she's an often overlooked scientist who in the 60s and the 70s made impressive and very important contributions to this kind of studies. And I'm very keen for her contribution, like that of many other women in science that are often forgotten or overlooked, to be acknowledged. But the idea is the following, that if you look at the galaxy, it's a spiral galaxy that rotates on its axis, spins around. So if we consider a star here at some distance from the center of the gravity of the galaxy, that star is being held on its circular orbit by the gravity generated by this inner part of the galaxy. At the same time, there's a centrifugal force that pushes the star outwards as it spins around the galaxy. And the two need to be balanced, or else the star would fly out of the galaxy if there wasn't enough gravity, or it would be falling inside to the center of the galaxy if there was too much gravity. And so because the visible part of the galaxy is concentrated in the middle, you can see here this bulge where most of the visible mass lies, as you move out and consider stars further and further away from the center of the galaxy, you'd expect the gravity generated by the center of the galaxy to go down, and therefore the velocity of the stars to diminish as well, because otherwise there isn't enough gravity, say, out here to keep these stars on track. So the expectation under Newton's theory of gravity, or for that matter, Einstein's, is that as a function of distance from the center, the velocity of stars should fall off. But observations by Vera Rubin and many others, and before her, Fritz Zwicky in the 30s, have consistently shown the velocity of stars to be fairly constant with radius, which is a real puzzle, to which there are only two logical solutions. Number one, Newton's theory of gravity and Einstein's theory of gravity are wrong. They do not describe what goes on galactic scales and beyond. But we've tested Einstein's theory of gravity very, very thoroughly in many different ways, and we're very confident it's a very strong, robust theory. Or, and here is the other hypothesis, there is more mass than meets the eye. This galaxy is not made only of the visible stuff that we see here. There's a halo of dark matter that is generating the additional gravity that's keeping the stars where they are. And that has been a very fruitful line of research for the past 80 years, despite the fact that we haven't found that dark matter particle yet. If it is a particle, we are getting closer and closer. And the discovery of dark matter is 5 years ahead, 5 years in the future, no matter when you ask. So I'm confident that in 5 years' time, we'll have it in the bag. And so the astonishing headline is that 96% of the universe is missing. All the stuff that's out there that we see, all this Hubble Space Telescope galaxies, are just the tip of the iceberg. Most of the universe is invisible and dark matter is one of the main components. And like we will see in a minute, if we go back all the way to the beginning of time in our quest to measure the mass of the universe, we pick up images such as this, which I'll explain in a moment, essentially a picture of the baby universe as when it was 0.1 per mil of its current age. And by analyzing this data and others from the universe, we've come to the conclusion the universe has got a dark side. And that is what we're interested in, because if we're trying to weigh the universe, we need to count everything, not just the stuff that we can see, but most importantly, all the stuff that we can't see. So here is a summary of what we know There's a lot that we know that we don't know about the universe today. All the galaxies in the Hubble Space Telescope picture are just this tiny little yellow sliver of the pie. There's more normal matter out there that doesn't show up necessarily in that Hubble Space Telescope picture, but we know of its existence. We think about 23% of the universe is in the form of dark matter, possibly a new type of particle that we haven't yet discovered, maybe 100 to 1,000 times more massive than a proton. And 73%, the vast majority of the universe, is in the form of something stranger still, dark energy, potentially something associated with the properties of vacuum, of empty space itself, which has quite different properties from dark matter. So how do we know all of this? Well, it all goes back to these two scientists. Here, Hubble, Edwin Hubble, pictured here in 1954, looking through the Palomar telescope, the Hooke telescope at Mount Palomar in California. And this gentleman here, who is not perhaps so much recognized as Hubble, Georges Lemaître, a Belgian priest and astrophysicist and mathematician who made very important theoretical contributions in cosmology in the early 20s and early 30s. And indeed so, in the last couple of years, the International Astronomical Union has renamed what was known as the Hubble law as the Hubble-Lemaître law, jointly acknowledging the role of both of them in finding out this law. And what does this law say? Well, it says that if you look at galaxies in the universe around us, all the dots in this graph, and those are the galaxies that Hubble observed in 1929 originally. He didn't know those were galaxies. He called them nebulae because nobody quite knew that the universe had other galaxies in it than the Milky Way at that time. So if you look at galaxies and you look at the velocity at which they are moving either away or towards us, you'll find that most of them, essentially all of them, are moving away from us with a velocity that increases the further away they are. So it appears as if the contents of the universe are expanding away from us, and they're going faster the further out they are. And this line here that Hubble drew through the data points is what we call the Hubble-Lemaître law today. The Hubble-Lemaître law we can understand better if we put together some pizza dough in our kitchen, because that turns out to be quite a good model for how the universe expands. So here's an expanding universe in your kitchen. You put together some pizza dough, and then you sprinkle it with olives. And our galaxy is the Milky Way here, the black olive. And as time goes on, as the universe expands, as space-time expands, all the galaxies are moving away from each other and moving away from us. And so if we look around us, we will measure all the galaxies' velocities to be moving away from us, and galaxies that are further away from us in a given amount of time will move further away and therefore faster than others because there is more space-time, i.e. pizza dough, to expand between us and them. What is also interesting about this model is that if you take the point of view of another galaxy, say this one here, an alien on that galaxy would see exactly the same picture as us. They also would see all the other galaxies moving away from them exactly as we do. We're not at the center of the universe. Every observer in the universe sees the same expansion of the universe, and that's because the universe itself is expanding, i.e. the pizza dough is expanding. And if you put this in the oven for 15 minutes at 200 degrees, and you take it out, you get a fantastic focaccia, which is always very good. And so if the universe is expanding now, if we rewind back the cosmic movie in time, it comes a point where all the galaxies were closer together and closer together and closer together until they were all heaped up in one point, which we call the Big Bang, the beginning of the universe. So from the expanding universe follows that the universe began at a certain moment in time, a moment that we can now measure quite precisely, thanks to these two engineers, Penzias and Wilson, who in 1964 discovered by mistake, in a totally serendipitous manner, the presence of a leftover radiation in the universe using this horn antenna here. It's a wonderful story, one of the great stories of science. They weren't looking for it, but they just stumbled on it, and they got the Nobel Prize for it in 1978 for discovering the leftover light from the Big Bang itself, proof that the universe had begun 13.8 billion years ago in a very hot, highly energetic state. And so if the universe began 13.8 billion years ago, and it has been expanding ever since, if we're interested in what's going to happen next, in the next few billion years, then we've got basically two different scenarios. Number one, the universe expands now, but gravity eventually takes over and slows the expansion down until the expansion stops, and then it starts recollapsing again into a big crunch, which is the reverse time sequence of the Big Bang. Or if the mass of the universe is not quite enough, if the gravity is not quite sufficient to stop the expansion, then the universe will continue expanding forever at an ever decelerating rate. So that goes back to the initial question of this lecture, weighing the universe, i.e. determining its mass. If we can measure the mass of the universe, then we will be able to tell whether that mass is sufficient for this to happen or not quite sufficient, and that will happen, and therefore this holds the key to the ultimate destiny, the fate of the universe. That's all very well, except there is a third scenario which is a little bit more exotic, bringing in dark energy. If dark energy exists, and it appears to exist, in fact 73% of the universe seems to be made of dark energy today, then dark energy has quite a different effect on the expansion of the universe. Rather than slowing it down, it's actually pushing it out and pushing it further. So the expansion is accelerating today under the influence of dark energy and has been for the past 6 billion years. If this is true, then the future is quite different. Dark energy will take over more and more as time goes on, and so the universe's expansion will not slow down, it will actually continue accelerating forever, and galaxies will move away from us faster and faster until we won't be able to see those galaxies anymore, because they will have been swept away by the cosmic expansion in such a way that not even light will ever be able to cross the increasing cosmic emptiness to us. And so that's a really important matter to understand whenever we go out and ask for funding to the funding agency for new telescopes and new observations of the universe. We need those observations now, because if we wait only 200 billion years, we won't be able to see those galaxies anymore. But the most important instrument in all of this is this, a picture of the baby universe gathered by a satellite called Planck, which was a joint effort by the European Space Agency and NASA. And this picture here shows the sky, the entire sky cut along a great circle and then laid down flat in a map for you to see. And it shows the universe as it was 380,000 years after the Big Bang, therefore at a fraction of its current age. What you're looking at here is the distribution of the light coming out of the Big Bang itself, effectively. This is light that you cannot see with optical telescopes. It's not visible light, it's microwave light. The same kind of light that cooks your food inside your microwave oven in the kitchen. And the little red spots are regions where that light is a little more energetic, a little hotter, and the blue dots are where it's a little cooler. And by little, I mean 1 part in 100,000. So it's very tiny little fluctuations. And yet, those fluctuations in the distribution of light coming from the Big Bang are absolutely essential in explaining why we are here. Because it is around the positive fluctuations where you got a little bit extra energy, a little bit of extra density, a little bit of extra mass. It's around those red spots that gravity does its job of accreting mass and thereby creating galaxies. And from galaxies, of course, habitable planets like the Earth, and therefore biological life forms such as ourselves. So what you're looking at here are the seeds out of which galaxies eventually grew, are the seeds that seeded galaxy, including our own eventually. So it's a very important map, which also depicts a universe much, much simpler than the universe that we saw earlier. It's a universe which did not contain galaxies yet, did not contain stars yet, did not contain elements like carbon, oxygen, or iron, or complexities like that yet, because they're not been formed yet. So it's a very simple universe that we can understand very well based on principles of physics. And not only we can understand it, we can map it out in great detail. You can see the exquisite resolution of this map that was obtained recently as compared to the earlier resolutions of earlier experiments. How technology has improved over time, enabling us to sharpen our view of that baby universe to an uncanny precision. And so thanks to this kind of observatories, we can look back all the way in time at the very beginning of the universe, essentially here at the end of the visible universe. And this is not a metaphor. This is the end of the visible cosmos, simply because before that moment in time, before 380,000 years after the Big Bang, the universe was filled with a hot plasma, a soup made of electrons and photons, which was opaque to light. Therefore, light could not travel freely before that time. The universe was like a glass of milk. You couldn't see through it. That map is literally the end of the visible universe, and we've mapped it out to exquisite precision. And it's telling us a very interesting story, if analyzed with the proper statistical tools, about the properties of the universe, the origins of the universe, the weight of the universe, or mass of the universe. Among other things, it tells us the age of the universe to a great deal of precision, 13,798,000,000 years, give or take 29 million years, which is nothing. Is nothing. This is incredible precision. We sit on the Earth and we do not know the age of this planet to this precision, and yet we sit on it. We can actually tell the age of the Earth, of the universe, to an incredible precision. It's like meeting a person who is 80 years old in the street, and at a glance being able to tell them what is their birth date to within a day of accuracy. Very, very impressive. And what this picture represents is very simple to understand using basic physics. It represents cosmic sound. In other words, the universe, before this picture was taken, the universe was filled with plasma, and that plasma was dense enough that it could support the propagation of sound waves, just like the air in this room propagates sound from my mouth or the AV system to your ear. And so those sound waves were seeded by quantum fluctuations in the early universe and then propagated outwards at about 1/3 of the speed of light. So very, very fast sound waves. And if I get only one quantum fluctuation, I get a nice spherical looking sound wave, just like when I throw a rock in a pond and I get a wave, a spherical wave going out in the pond. But if I throw many, many rocks in the pond, then the superposition of these rocks will create a pattern, which is exactly the pattern that we see in the microwave background map, as it is called, that I showed you before. So the hot spots and the red spots corresponds to places where those waves were a little bit higher, so crests in the waves or troughs in the waves. And when you have many such waves, you superimpose them randomly, you will get a pattern that resembles the one of the red and blue spots that I showed you earlier. So effectively, by looking at this plot, you're looking at sound waves traveling at this very high speed in the early universe. And we can analyze them statistically to bring out their sound characteristics, to bring to the fore the physics behind them. So at the top, I've given you a plot of a sound wave, as we are used to seeing them, perhaps. At the bottom, a plot representing essentially a statistical manipulation of the image of the relic radiation from the Big Bang. And what you can see is two stunning things. The first, this picture looks very much like a sound wave, doesn't it? You've got sound, clearly oscillations. They're not exactly all the same height, and we understand that in great detail too, but they're clearly not random. There is a sound pattern embedded into this picture. The second thing I want to draw your attention on is, I think, one of the greatest triumphs of modern physics, irrespective of field. The red dots are the observations from the Planck satellite. Those are data. The green line is our best model. And it goes through all of these dots. And that model has got 6 free parameters, 6 numbers that you can tune. And there are thousands of dots in this picture. We can explain them all using just 6 numbers. Among them, dark matter, this 23% that we've been talking about, and dark energy, 73%. If you didn't have dark matter and dark energy, your green curve would not go through the dots. Simple as that. Those dots have errors. The errors are too small to see. That's the uncanny precision with which we can measure and understand this primordial light that has been traveling for 13,800,000,000 years before falling into our instruments. So that's great, except it leaves us with these big questions. We can understand this, but it still doesn't make sense. 95% of the universe that we need to explain this data is dark and, as of yet, undiscovered. Be as it might, we need to account for it if we are to weigh the universe. How do we do that? First of all, how do we take the universe and make a weight measurement or a mass measurement, if we want to be precise, of the universe, given the fact that we certainly cannot take the universe and put it on a set of scales? And so for that, we need to remind ourselves of a different perspective, the perspective of an ant. Because that's what we are. We are ants, not on the surface of a flat surface like real ants might be, but we're ants living in three-dimensional space, which we cannot leave. We cannot step out of the universe, just like an ant cannot step off a tennis ball, for example, to look at it and understand what its shape is. And the shape is important because just like Einstein told us, the universe's shape is a reflection of its mass. So the more massive the universe, the more bent its shape will be as a whole. And in fact, it turns out that for the kind of universe we live in, there are only three possible shapes. Now, I cannot depict three-dimensional shapes on a two-dimensional screen, but I can give you a two-dimensional analogy. And the three analogies are that of Euclidean flat space, just a table like this, a tennis ball, positive curvature, or a saddle, a hyperbolic space. So in this analogy, we are like the ants, except our space, of course, is three-dimensional. This space is only two-dimensional, but this is the analogy that we can work with in order to picture the idea that we want to be able to measure the shape of the universe, the geometry of the universe, which is, Einstein tells us, connected to its mass contents. And if we can measure the shape, we can infer the mass, job done. So if we are an ant, how are we going to do that? Because we cannot step out of the universe and look at it and determine which of the three cases we are in. But fortunately, we can use geometry and to rescue us from this conundrum, namely the fact that parallel lines in a flat space stay parallel forever. So if you set off in two parallel directions, you will never cross. In a positively curved universe, if you set off from the equator and you can just keep going straight, eventually you'll meet at the North Pole. And that tells you that the surface of the Earth is curved. It's not a flat space. In a hyperbolic space, the opposite happens. Your distance increases as you go along, despite the fact that you're on parallel lines. So can we use this trick for the universe then? And so here is the analogy, again, flat, open, and closed. Now, in order to use the ant trick in the universe, we have a great deal of road or space to cover. Remember, the nearest galaxy is 2.5 million light years away. The microwave background, the baby universe picture, is 13.8 billion years old, but in the meantime, that region of space has expanded because of the expansion of the universe. That part of space is now 46 billion light years away. We cannot cross that distance in any possible way. So actually, using the ant trick is not practical because we can't traverse a big enough part of space for the effects of the geometry of space, if any, to be felt. We need something else. And that something else is the geometry of triangles. Again, geometry tells us that a triangle on a flat surface has got angles that sum up to 180 degrees, a geometric fact that you might remember from school. But spherical geometry is different. The same triangle, when drawn on the surface of a sphere, has got fatter angles. And if you sum up the three angles of that triangle, you get more than 180 degrees. And vice versa, a triangle on an open hyperbolic space has got thinner angles, and the sum of that angles is less than 180 degrees. So here's another method then. If we can draw a big enough triangle through space, and we can measure the angles of that triangle, the sum of the angles tells us the shape or the geometry of the universe. And that is connected to its mass. So geometry is mass connected to mass, and mass is both matter and energy. E equals mc squared, so energy counts as well in Einstein equation. And so perhaps we can use the microwave background light from the furthest possible regions of the universe to help us with that. Because that microwave background light is not uniform, it's got little spots on it, the quantum fluctuations we talked about. And the apparent distance of these spots changes depending on which kind of geometry the universe has got. So in a universe that's flat, like this, the spots will be distributed in an apparently random fashion, but the distance between them will be of a certain order. If we go to a universe which is like this, the same spots will be blown a little bit apart by the geometry of the universe. And so you can see that these two patterns look different. And in an open universe, again, the spots will be actually closer to each other. So by looking carefully at the distribution of spots, we can use the spots as a measuring device for one of the sides of our triangle, and therefore use them to measure the shape of the universe, the geometry. So here's the idea. We want this big triangle where the far end of the triangle is 13 billion light years in the past, is the distance between the spots in the microwave background. The other two sides of the triangle are the sides that the light has been traveling on to get to us, from here to our telescope, from here to our telescope. We know how big this side is because we know what is the edge of the universe, we know what the distance is. And so we have a big triangle, a triangle whose small side is the distance between the spots, and whose big sides are the distance between us and the cosmic microwave background. And so those spots here are the reflection of a wave. So essentially, the distance between spots is the distance between two crests of the sound wave. How big is this distance? I told you it was a big wave. It's a sound wave, all right, but it's not the same sort of distances as the waves, the sound waves that we are used to. This is the number of kilometers, how big that sound wave is. I can't really read this, but it's a very big wave. And that big wave gives us the small side. We measure that side because we know the distance, and we can work out the angles of this triangle. And here is the solution. We find that the quantity, the number that controls whether we live in a flat, a closed, or an open universe is very, 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 very close to zero, where zero corresponds to a universe that's perfectly flat. So within the precision that we can master using our technology and measurements today, to better the 1 per mil precision, we live in a flat universe. And that seems rather interesting because a flat universe is only a special case. The universe could be closed and with a certain shape, or open in a certain shape, but it appears to be very, very nearly to flat. We can understand this if the early universe started off being perhaps closed, or open for that matter, but with a non-zero curvature, and then was blown apart, was essentially expanded by a very large amount in a very small time. And therefore, a ball like this, which has got a non-zero curvature, if blown big enough, will look completely flat to any observer. Just like here on the surface of the Earth, we look around us, we don't see the curvature of the Earth, because the Earth is big enough for that curvature not to be visible locally. Of course, if you go to the top of a mountain or on an airplane, you will see the curvature of the Earth. But for the universe, the part of the universe that we can see, the 46 billion light years across, is a tiny little circle on a much bigger universe. And therefore, the curvature of the universe has been diluted away by a very fast expansion that we call inflation. At the very, very beginning of the universe was expanded mightily by something that we still don't understand, probably a new type of a field called a scalar field that has made the universe appear to be very, very flat today. And so here is the picture that I want to leave you with, the picture of all we know and all that we don't know about the universe from its very beginning to today. So the universe starts with a Big Bang. Very little is known about the moment of the Big Bang itself. We simply do not have the physics necessary to understand time zero. But we understand and can explain much of what happens starting from 10 to the minus 32 seconds after the Big Bang until today. Inflation is this moment where the universe expands exponentially to become almost flat, or essentially indistinguishable from flat. For 380,000 years, the universe is filled with the cosmic plasma that then gives rise to the relic radiation that is the microwave background. 500 million years or so of dark ages where the universe doesn't contain any stars, but just gas that's struggling to get together and form stars. The first stars are then formed from their galaxies, and then today, 13.7, 13.8 billion years later, here we are looking back at it and marveling at the complexity, but also the simplicity, and more than anything, in my opinion, marveling at our ability as humans to be able to look back all of these vast distances in time, vast scales, vast differences in energy, and understand it all, which is our quest to understand the fundamental nature of reality. And here is the final answer. We started off by asking, what is the weight of the universe? Then we understood we actually had to talk about the mass of the universe, but that's not even the right question. Because if you think about it, if the universe is flat, then it's also, according to Einstein, infinite in extent, in spatial extent. And an infinite universe certainly has got an infinite mass and always has had an infinite mass. So the mass of the universe per se is not the right number. What we need to measure is the mass density of the universe, namely, on average, how much mass there is per cubic centimeter or per cubic meter, or for whatever unit you care to measure it. And that's the answer, is this number here, 10 to the minus 27 or so, gram per centimeter square. It's an almost, it feels almost empty. And certainly here in this room, the average density is much, much higher than that. But on average, the universe is almost empty, but finely poised in such a way that this number here, made of visible matter, and dark energy, all together makes the universe flat, a universe that's simple, understandable, and frankly, quite amazing. Thank you very much.